All right, here we go. All right, so today we'll talk about some graph problems again. We all like graphs. But this is continuing this theme where we're looking at problems that aren't necessarily so easy to solve, right? Starting from just trying to decide if a Boolean formula is satisfiable. We don't know if there's a polynomial time algorithm. Even for special cases like 3-sat, we do know that there's a polynomial time algorithm for 3-sat if and only if there's one for all Boolean formulas, which is a different kind of result. We did this 2-sat versus max 2-sat thing, right? 2-sat you can actually solve, max 2-sat you couldn't. And then last time we did subset sum, which was same things, but was kind of more of a departure because subset sum, at least to me, doesn't look anything like sat, right? Because like numbers and stuff. But if you scrutinize it and you're clever, you start realizing that you could use numbers to start packing in a lot of logic. Yeah, we kind of rewrote sat as a bunch of elementary rules and use one digit for each rule that we wanted to satisfy. Yeah, so that's sort of like surprising and should suddenly start making you wonder about all sorts of things, right? If suddenly subset sum can pack in a ton of complexity, then where else can complexity be hiding, right? So it's saying that this simple looking question of just adding up numbers to a target, which is like the simplest question you could almost think of, um, is quite general, right? It can be quite general, at least if we're looking at this kind of model of computing, this polynomial emphasis, stuff like this, right? So some of we're also kind of exploring uh, the implications of just some of these simple definitions. If we focus on polynomial running time and the input, we get these funny consequences. Okay, so today's problem is quite similar to something we did a couple of weeks ago. So we used to do shortest path in a graph. Today we're going to do to find the longest path in a graph. And to be clear, path means you don't repeat vertices. Okay? Walk means you can repeat vertices. Path means they need to be distinct in our class. So a special case is a Hamiltonian path, which is named after some guy named Hamilton. But that means you visit every vertex. Okay? Um, so I can give you a graph like this one and ask you what is the length, say number of edges or vertices or whatever. It will be off by one of the longest path in this graph. All right, one guy's out. Uh, Six. You got six, 9. Anyone get 9 or beat 9? It's also hard to count past 9, honestly. But okay, so let's try. Let's go with the 9. Where should I start? We'll see if it's actually 9. This one? This one. Okay. All right, so from here, should I go, I guess, down left, up right, right, up, right, down left? You can't revisit the same vertex. Oh, so I'll undo this whole thing. Do you guys want to start here or start somewhere else? Upright? Down? Okay. Oh, this is 6, right? We can go this way. Go like that. That's 6. We can start here. Okay, so we got 8. No, I can't count, can I? 7. Oh, it's 8. Yeah, okay, it's a little confusing. It is 8, I think. Something weird about those colors. Oh, sorry, 8 vertices, 7 edges. All right. Anyone at least maybe based on this, see how we can do better? Maybe some local adjustments. Like, what if I had instead gone up? Would that do better? Oh, and then you start going here, and then you recover. Okay, yeah, so it looks like we can do this purple detour. That'll get us a few more. Hmm? That would be 8. It was starting from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I might have miscounted, but if you start all the way from here and you go here, here, and then so we got 10? That's not bad. Yeah. Okay. I don't actually know what the right answer is. Uh, but 10 might be the best I've seen. But this problem's very tricky, right? Um, okay. So, so we're going to look at this problem in 3 settings, and then we'll do some comparative discussion. In DAGs, directed acyclic, so no cycles. Uh, directed graphs is probably the most general, and then undirected graphs. So for each of these graphs, do we think we'll get a polynomial time algorithm, or do you think it'll turn out to be as hard as SAT, right? And as usual, you don't have to vote. Okay. So first off, who is not voting? Sorry, I don't mean to always look at you, but okay. Let's do DAG first. Who thinks we'll get an algorithm for a DAG? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And who doesn't? 2. Okay. And then what about directed graphs? Who thinks we'll get an algorithm? 1, 2, 3, 1, 2, 3, 4, 5. Yeah. And then who thinks it'll be hard? 1, 2, 3, 4, 5, 6, 7. Okay. Okay. And then what about undirected graphs? Who thinks we'll get an algorithm? 1, 2, 3, 1, 2, 3. And then who thinks it'll be hard? 1, 2, 3, 4, 5, 6, 7. I mean, it always adds up to 12, but sometimes it doesn't. Wait, no. Did I get this wrong? Wait, who didn't vote? Oh, okay. All right. Which one is that what you wanted? Hard? Okay, yeah. So what was the point you're bringing up? Huh? Yeah, so if we could solve directed graph, then I should be able to take an undirected graph and just for every undirected edge, add both directions and then feed that into the directed graph. Right? So we probably should not have a smaller number. Uh, um, fatigue. Oh, so you guys just thought like, oh, it's going down 10, 5. It's like about why people are morons. Uh, okay. Okay, that only explains one vote. But there's a discrepancy of 2. So there's at least one person who, yeah. Okay. So you just panicked and picked hard and sad. Okay. All right. Good. Okay, so let's look at longest path in a DAG. Okay. And well, the first maybe basic thing I want to point out is there's no cycles, so any walk is a path, right? So I could have also called this longest walk in a DAG. Okay. Okay, so most of you thought that we could get an algorithm. If so, what are some ideas? Yeah. Okay, so if you take a topological sort point of view, you should, okay. So I'll take some kind of topological sort, right? So there'll be some edges going from left to right. And you probably want to do just focus on the sources or something, right? But you said we should run BFS from the sources and get distances to everyone else. So like take this leftmost vertex, I'll run right BFS, I'll try to find the shortest path to every other vertex, right? But that means if you have an edge like this, say you have something like this, you have lots of edges in between or something. So the longest path, will be going through a lot of vertices. Okay, some kind of dynamic program, or yeah. Okay, so that sounds like some kind of induction or maybe the bottom of a recursive algorithm up. Yeah. Oh, okay, maybe something like longest increasing subsequence, but I can imagine laying out the vertices and saying, give me the longest vertex starting from here. So the longest increasing subsequence I go down, I compare everything to see if I can go there. But here, I guess you just go down and see if there's an edge. In fact, you could almost go, the vice versa is almost clear. You can imagine doing longest increasing subsequence, but then thinking of that array, each slot as being a vertex, and then drawing edges if it's, so we can imagine, if the number is going up, and then you could take longest increasing subsequence, make it look like a longest path problem. Yeah. Yeah. But that's very similar to dynamic programming. Okay. Uh, we'll have to figure that out offline. Yeah. Uh, yeah, I guess the Lenin thing threw people off. Uh, that was just the Wikipedia article. That was the whole thing. Uh, okay, so let's try to do a recursive algorithm, in which case let's do or dynamic program, but we'll start with the recursive. And I think if you look at it from bottom up, it'll be similar ultimately to what you had in mind. So if so, we need to come up with some spec first. Yeah, so maybe I'll do LW for longest walk. And now who wants to pick some parentheses in a sentence? Yeah. hmm Longest walk from V. From V? Okay. Yeah, so this makes sense. I'm here and I want to get the longest walk and maybe, well, we'll implement it now. Okay. Right. So if I want to implement this, what should we do? Or some base cases or whatever? Yeah, so maybe zero if V is so then we just say V is a sink. Another word for this. Okay, good. Otherwise, yeah. Yes, I think you want to look at this and enumerate over all the edges, right? So maybe I'll write max over all edges V, W, and E. So all basically W or VWs and E. 1 plus the longest walk from W, right? Maybe this is W or something. Okay, simple enough. Okay, so that would be such an algorithm. Now, what would be the running time? Right here, I'm just summing up the running time for each subproblem. Okay, why n squared? Yeah, okay, so if each vertex has at most n edges, and there's n of them, you get n times n, right? Okay, but if we look closer, we can get it to a slightly smaller number, maybe. Like you said, we're summing up the out degrees of the vertices, right? Or 1 plus the out degrees. Yeah. So if we sum up the out degrees of all the vertices, we'll count every edge once. So we can get that n squared down to m. N squared, of course, is an upper bound on m, but sometimes m is smaller. Okay, good. Simple enough, right? So this problem is actually quite easy on a DAG. It's almost like the only recursive algorithm you could do in some sense. Yeah, but then DP makes it fast. So this is actually a very interesting point. Uh, so what does this DAG structure, right? The lack of cycles represent, right? Or topological order, right? It means you can do recursion like very easily. Or you're worried about infinite loops when you do recursion, right? But there's no cycles in the graph. So many problems on DAGs are very naturally, you can do recursive. You just kind of propagate through the graph and you save your answers. Yeah. So there's a whole family of problems which you'll find at the end of the of the chapter, um, where there's all these kind of tough problems, but they might be easier for a DAG. Yeah, and there's some kind of dynamic programming you can do. And you might find that many of the dynamic programming problems you've done before, you could imagine like the underlying subproblems having a DAG-like structure, right? Like longest increasing subsequence, I'm always looking at the suffixes. I think of each suffix as a node, dependencies are acyclic. Maybe that's a little abstract, but whenever you have some kind of implicit DAG structure, right? So it might be a big word problem. You might not see the DAG right away, but you study it closely and you realize there's no cyclic dependencies in this word problem or some clever way. Then suddenly you could potentially do a very fast algorithm. Yeah. So that's something to keep an eye out for. But you get a lot of practice to make practice this distinction. Okay, good. So this did have a polynomial time algorithm. So now we're on to the directed case, which I think this was 5 to 7. Okay, so a little more than half thought it would be hard. Okay, and indeed that's what we're going to try to show. Okay, we're going to try to show that a polynomial time algorithm, and we'll just actually focus on the special case of is there a Hamiltonian path? Okay, so that's even easier. If you can solve longest path, then you can figure out if there's a Hamiltonian path, because Hamiltonian is like the maximum length, right? But if we can show that finding a Hamiltonian path is hard, that would, of course, then automatically show that finding the longest path is hard. Good. All right, so we're going to start with a SAT formula. We're going to somehow try to come up with some kind of graph, right? Because you have a black box that takes as input a directed graph. And you ask the black box, is there a Hamiltonian path? And it answers yes or no. And you're hoping that gives that yes or no will translate to the SAT formula. Okay. So the real thing is, how are we going to take a SAT problem and encode it in a graph? Just like how last time the challenge was, how am I going to take a SAT problem, a complex, many variables, many rules, and encode it into numbers getting added up. Now we got to figure out how to make graphs or show that graphs are in fact can be very expressive. Good. So, all right, here's maybe a starting point, right? I don't know if add the graph is the right phrase. Maybe I should have wrote graphically, but you're given some formula and you have a bunch of yes or no decisions for every variable, right? Maybe we'll start there. And how can I try to express this graphically? Something related to longest path stuff. I guess I should have just said, any ideas for how to start with a reduction? This would have been the first hit. Yeah. Okay, so yeah, uh, one for each one. Hmm. Okay, or let me say, what are the decisions you make in a Hamiltonian path problem? Like whether or not maybe they traverse an edge. So maybe like somehow like if our choice is like take this edge or take that edge, somehow that gives you, yeah. Yeah, maybe I can imagine something like this means true and this means false for some variable x1 or something. Sort of like an implication graph. Yeah, yeah, not clear sometimes. Let's see. This is what we're actually going to try to do. Okay. So what we're going to do for every variable is I'm going to make a very long path with edges in both directions, right? And keep in mind that any Hamiltonian path has to visit everything in the middle. Okay. So any Hamiltonian path is going to have to go all the way through in one direction or all the way through in another direction to visit everyone in the middle, if this were the entire graph. Okay. This is what we're going to try to do. We are going to, uh, if we set something up like this and say, oh, going from left to right, I can think of that as like x1 to be true, and going from right to left as sort of, or maybe you're going from top down, going from right to left. This is sort of the algorithm saying I want to set x1 to be false, right? And so that's the starting point where we try to encode some kind of decision making. So the algorithm is trying to find a Hamiltonian path, and we want to encode this. You have to choose true or false. It may not make much sense yet because it's only an isolated part of the whole thing. Okay, so, okay, is it version left to right or from right to left? Okay, so that's how we're going to kind of set up our graph initially. We're going to make this huge ladder-like structure. Okay, and so the idea at this stage is a Hamiltonian path needs to start at the top because it needs to visit every vertex. It needs to make it all the way down to the bottom. And along the way, for each variable, it needs to choose whether to go left or right, left or right. And that is going to be implicitly choosing x1 to be true or x1 to be false, x2 to be true or x2 to be false. Yeah. Yeah. Okay. So the awkward thing to get us started is we're trying to somehow we're trying to get this black box that only looks for Hamiltonian path to effectively solve a SAT problem for us. Okay. So the first gadget is trying to figure out how to make some kind of graph where I can sort of read off a binary yes or no decision, true or false decision for every variable. And so the high level idea is if you make a long path with edges in both directions, there's all these vertices in the middle that a Hamiltonian path will have to visit. Okay. Yeah. So I'm making the graph. Yeah. And so the idea here is a Hamiltonian path is going to have to go all the way through from left to right, or all the way through from right to left, just to visit these intermediate vertices. Yeah. Oh yeah, yeah. So these middle nodes was two edges in the middle. Whatever direction you go in on, you have to leave in the same direction because you can't go backwards in a Hamiltonian path. So it's kind of getting it to commit in some way. Okay. So the initial part of our construction, we haven't done anything about the clauses yet, okay, is to take all these paths and hook them together like some kind of ladder. So Hamiltonian path is going to have to visit all of the rungs. And for each rung, it needs to decide whether to go left or right. So it could start in either corner it wants to, and say it goes from left to right or something. But then I added these blue edges so that on the next rung, it can choose which side to start on. So even if it sets x1 to be true, it can make x2 to be false, or it can set x2 to be true. Okay, yeah. Yeah, right now a Hamiltonian path will exist. It just winds its way all the way down in any direction it wants. Yeah, just like how a SAT formula was no clauses, anything would satisfy. Yeah. It can go straight down, yes, but then that won't be a Hamiltonian path. So the black box, you ask it, is there a Hamiltonian path? So it will try to find one if one exists. I mean, there's all these vertices in the middle of those rungs. The red things are vertices. Oh, okay, okay. So the blue things are edges, and the red things, the dots are vertices. So just to visit, a Hamiltonian path needs to visit everything. So it needs to make its way through every path. Yeah. Oh, yeah. Yeah. So for every variable, I've created a path to try to model that variable. Yeah. Sorry? So I just think of the first path as my path for x1. The second path will be my path for x2. The third path, yeah. Maybe it'll make a little more sense when we see the next stage, because then it'll motivate why we're doing this a little better. Yeah. So, okay. That's how I want to model choosing x1 to be true or false based on the direction you take in the Hamiltonian path. The Hamiltonian path really needs to commit to one direction or the other, at least at this stage. Okay. So now the question is, how are we going to incorporate clauses? Yeah. So as pointed out, there's a gazillion Hamiltonian paths because you can find it any way you want down the ladder, right? So now we want to add maybe a few more vertices and edges or something, right? And it should somehow be like, oh, you can only satisfy this clause if you're, setting x1 to be true or something. Okay? So yeah, yeah. Sorry? Sorry, say that again? Yeah. Oh, so it's like if you set x1 to be true, then you can't set x2 to be true. So I'll delete one of these edges. Um, uh, I mean, maybe you could, but I don't know if it's expressive enough. I mean, in that example, I gave you a two sat clause with x1 and x2. So you could do it for that special case, but in general, you have more variables in the clauses, and it might not be the consecutive variables either. Yeah. Yeah, you can choose it. The question is there a Hamiltonian path from any vertex? Because the idea being that, let's say you go from left to right because you set that x1 to be true. you should be allowed to set x2 to be true or x2 to be false. So if you want to set x2 to be true, you need to take that edge going back to the other side, or x2 to be false, you go straight down. Yeah, it's just to permit those choices. Okay. But now I want to try to figure out how to add my constraints. Yeah. Yeah, so maybe this is misleading. Let me uh so maybe here, I mean, so this is not very easy to guess or anything. It's partly because if you try, then you're more likely to remember it. But maybe one thing we could focus on is like, well, choices should map to choices, requirements should map to requirements or something, right? So you're required to satisfy this clause in SAT. In Hamiltonian path, you're required to visit all the vertices. So at least one idea is like, oh, can we try introducing a vertex for each clause, right? Because you have to visit it. But maybe we can somehow figure out how to hack it so that you can only visit it if you're making the right choice in terms of the Hamiltonian path stuff. Yeah. Right, exactly. I should only be able to visit that vertex if I'm taking the x1 equals true direction or the x2 equals false direction, right? Yeah. Yeah. So did you also was there a new vertex in your idea? Okay. All right. So yeah, so we're going to try to make a new vertex that you can visit only if you're setting the appropriate variable, right? So going back to this example of x1 or not x2. So let's just focus on those two rungs of the ladder. Okay. So I imagine something like this. So there's a new vertex in the middle there, that purpley maroon thing. Okay, but I haven't drawn the edges. Okay. We should draw the edge in a way where you should only be able to satisfy it. You should only be able to visit if you're going the right direction. Yeah. Oh, I might have flipped the sign somewhere. Like this, something like this, right? So if you're going in the correct direction for this clause, I somehow changed the clause subtly on you, so now it's not x1 or x2. But if you're going in the x1 equals false direction, which is, I guess, that way, then it's easy to drop by, visit this vertex on the way. If you're going the wrong way, you can't. Okay. And same with x2. If you're going in the x2 is equal to true direction, then you can easily drop by and visit. If you're going the wrong way, even if you went backwards, then you're screwed. Yeah. Yeah. So how do we prevent things like going from here to here to here? I should have done a different color. Something like this. Doesn't do what? Yeah, so we want to make it so then you should, if you do that, you'll probably never be able to get back to here. Unless there's some other way to, yeah, or you can't get back to both here and here. It's possible there's some weird Hamiltonian path that ends here, but then you have nowhere to go. Oh, these light blue lines? Okay, so what do I want to do? Oh, like this? Add all these edges? Uh, so that's risky because it means you can start like you can do whatever you. So the nice thing about, well, maybe not. I mean, but the nice thing about having it constrained is that you want to limit the Hamiltonian path, right? So that we can really get it to force it to solve our SAT problem for us. So adding those extra edges, even if it still works, would just make it a little harder to argue that it's not cheating in some way because we give it all this freedom if we did added those edges. Yeah. Okay. So if the clause was like that, yeah. So that means that the Hamiltonian path is going to be going in this direction here, and so it can easily just visit along the way, right? And if x2 was false, then the Hamiltonian path later on will be going like this, and it won't be able to visit the middle vertex. It'll have to bypass it. That's okay, because you were able to visit that vertex when you were doing x1. Or yeah, yeah. So the whole thing might look something like this. Yeah. So you're gonna have solutions that are like, oh, you walk here, you visit here, you go all the way there. Now you finish row one, and now you get to make a choice. For next one, maybe you go this way. You go here, you visit this, you go back, and you go over here or something, and then you go down. Um, no, that's got to be a mistake. Yeah, you're right. So maybe it's like this or something. Yeah. The middle route. So there's probably not enough clauses on this picture to make it look all that difficult, right? But ultimately, each direction you choose is going to be forcing you to choose. I mean, you're ultimately just solving a SAT formula. And here it's just a SAT formula where there's like fewer clauses than variables the way it looks. So it doesn't seem very interesting. Yeah, something like this. Yeah. Now there's certain you have to make sure you have enough as many vertices as clauses, right? So the picture I drew is not quite representative because you want to use a different pair of vertices for each clause, stuff like this. But otherwise, it's not that big a deal. And it takes a little care to get down on paper, really showing that you have to traverse the graph in this particular way, or else you couldn't possibly get the Hamiltonian path. So it's a little cumbersome to get it all written down, uh, if I remember correctly. Okay. Um, but that's the idea. Yeah. So we create this thing, and we create these gadgets. Okay? But it's very clever, um, and fun to draw construction. Okay. So that's yeah, skipping something for, oh yeah, so I should mention that yeah. So if you make the rows wide enough, you're gonna use a pair for each clause. You're gonna get a whole graph that has maybe size mn, because you have roughly n rows, and you're gonna have n vertices in the middle. Okay, so about mn size graph. Okay, so that's how you can show the Hamiltonian path is just as hard as SAT. Yeah, but it's incredibly clever, right? And then now and it makes you realize, oh, okay, now you start thinking, oh, I could play lots of games with graphs, and graphs are quite expressive too. It's just like a foreign language. It's not as natural as Boolean algebra, but it's still a language. I mean, that seems to be a high level kind of what's going on. Is like It seems you can't just assume you can answer all questions. In Boolean algebra, you can pose all these questions, right? And that makes you a little bit worried. The surprising thing here is that, oh, if you're very clever, you can actually pose those same questions as graphs. Yeah, some of the graphs aren't quite as easy as we thought because they encompass quite a bit more than expected. At least in in the context of longest Hamiltonian path, we have this requirement where you can't revisit vertices. This is a sharp contrast to shortest path. Right, shortest path, no problem. Longest path, world of hurt. Okay, so this comes to our most controversial vote, the undirected graphs. Okay, maybe I could take the vote again. Do you have enough time? Yeah. And there's no psych here because there's no numbers up there, so that's also cleared. So we have a clean. All right, who thinks that undirected is going to turn out to be hard? Oh, 1, 2, 3, 4, 5.5, 6. Okay, 6. And then who thinks we'll get an algorithm? 1, 2, 3, 4, 5. Wait, no, we're missing a vote. No, no, no. Last time we had 5 here, so it just can't be less. If we did less again, then I think I failed as a teacher. Uh, okay, someone didn't vote. You didn't vote, did you? Yeah. Oh, you said hard? Oh, was it 7? Okay, okay, whatever. We'll figure it out. Okay, so undirected graph. Okay, for those who thought it was hard, any intuition behind or gut feeling or psych explanations? Or for those who thought we might have an algorithm, any ideas for an algorithm? Yeah, yeah. So that's an Eulerian tour. An Euler, yes, it's something. It's called an Eulerian tour. The same Euler of Euler's constant is visiting every edge exactly twice, once in each. No, no, it's visiting every edge exactly once in one direction or the other. But that's a different problem because you can revisit vertices. Uh, and that we do have an algorithm. It turns out if you just count the degrees and they're even, you're okay, right? Basically, you go in and out, and what's left is even degree left, and you can just do induction. Oh, okay, yeah, yeah. Sorry. H. Okay. How do you guys know these names? I don't know these names. Okay, on the Wikipedia page. Okay. Yeah, so highlight Euler you can do, and I guess that's an undirected graph, so maybe you're hoping that was the key to that problem. Okay, that's reasonable. Okay. It will turn out to be hard. Okay. And I get the obvious candidate to show it's hard is to start from the directed setting, right? That seems the most similar. Okay, so this is guessable. Okay. So, all right, you know that directed Hamiltonian path is hard. I want to show that undirected Hamiltonian path is hard. Yeah. Okay, so you start with a directed graph, so the idea is to just add all the opposite. Okay, so let's say that you add all the opposite edges and you find a Hamiltonian path in this undirected, or another way to think of it is to forget all the arrows, right? You forget the directions of the edges. Okay, so one idea, which is actually how I drew the picture on the right, right? I just erased the arrows. Okay, so so let's say that you forget all the directions and you feed it to your black box and it says, well, if you're not worried about directions, then there is a Hamiltonian path. What does that tell you about the original graph? Yeah, it doesn't necessarily tell you that there's a Hamiltonian path in the original graph. It is true that if the black box said no, then there would be no, but yes does not mean yes. So we'll have to be a little bit more clever than that. Yeah, yeah. So undirected is a special case, right? Undirected graphs are directed graphs, so you can think of them as directed graphs that always have both directions. But directed graphs aren't necessarily undirected graphs, right? Square is rectangle. Yeah, it's definitely tricky for the reasons you outlined. Yeah, yeah. Okay. Uh, I'll do T and S. Sorry. Is that a vertex? Okay, so imagining something like this, and if there's some other vertex X, this will go to like X in, something like this. So one sec. Okay, so you can take something. I think this is the idea that you had in mind. So here's your typical prototypical vertex with some edges, and we're going to try to split them. Okay, so I'll do something like this. That work the way I wanted? It does. Okay, and I'll add a new edge here. Okay, and that means like if there's another vertex over here, right? So I'll call this like the in version, V in, V out, and this is just V or something, right? And if this was X, this will go to X in. Okay, but our graph can't have direction, so these now need to not have arrows. Can I control that? I don't think so. Okay, so these will become undirected edges. Okay, something like this. Okay, now, so I guess the idea is that your Hamiltonian path or whatever is coming in like this, and then you want it to go this way, right? And then it'll keep going. And you're trying to force it to traverse the middle edge, right? That kind of makes sense. You can imagine doing this graph and at least mapping a Hamiltonian path in the directed graph onto a Hamiltonian path in this graph, right? But we should be a little bit careful because what if you have a Hamiltonian path in your undirected graph that goes like this and like this, right? And it's not clear how to recover because you want to be able to take your Hamiltonian path in your undirected graph and recover a Hamiltonian path in the original graph. Okay. Okay. So we'll put one more vertex in the middle. Okay. So now something that comes in on one side. Oops, I can't do that. Now you really have to go somewhere. Yeah. Okay. So now if you look at this, so all right. So the way this is structured, this is going into the in vertex of another. So you always be going from out to in, and then into mid, mid to out, out to, or in reverse. You could be going. You can read it in either direction, but you always have to have this same ordering of the in, middle, out, one direction or the other. So, and we get to choose the direction we interpret. So we can just interpret it in the forward direction. Yeah, because it'll have this fixed pattern. Yeah, question. Oh, ends in the middle or starts in the middle? Yeah, so maybe you have to be a little bit more careful because like maybe you could cheat. Oh no, I shouldn't have. Okay. Maybe you could cheat if the Hamiltonian path like started or ended here, right? Because then if it goes off like this, then later it can go like this. Yeah, okay. Any ideas? No, you can't restrict because the black box is only doing something specific, right? Because we want to show that this very specific looking, limited looking problem can in fact solve something very general. So we don't want to add rules. Make it worse. Oh, we can add a source vertex. Yeah. So if I imagine this was the undirected graph that we made, I mean, it doesn't look like this split graph, but the suggestion was maybe we can add a source vertex and a sink vertex. The source will be connected to everyone. Will this work? We should be careful. And the sink will be connected to everyone. Okay, but now we want to be a little bit careful because we don't want the Hamiltonian path to go like this. We can add more sources. Yeah, something like this. And now the only way to get to S prime and T prime is to start and end there. I think that works. I think there's many ways to fix this, but this is just one hack. These are all kind of hacky. There's nothing special about these particular reductions. They're all messy. Yeah. Oh yeah, this should only connect to the end vertices, V ends, and these should only connect to V outs. Yeah. Yeah. Absolutely. Good. Now I know you guys know this better than me. Okay, that's great. Okay. So now any path, Hamiltonian path that starts at S prime and ends at T prime, or it's undirected originally, but you can interpret it as going from S prime to T prime. For you, it's like this, yeah. And it's going to visit in one first, and then it's going to have to do the thing like we expect. Okay, so this is often the case. You have the right high level idea, and there's just like one or two details left. Just got to get those down. And ultimately, to do a full proof, we have to do the mapping. So I would start with a directed Hamiltonian path in a graph, and I would map it to a Hamiltonian path in our clever split graph. And vice versa, I would take the Hamiltonian path in our undirected split graph. And first, I need to point out that it must have this structure. It starts at S prime, ends at T prime, and it visits the things in the middle, because otherwise you wouldn't, in the order we expect. Otherwise, it'll miss the middle vertex or something. And then you can just read off the order of the vertices that it visited. That's your directed Hamiltonian path. This is a little cumbersome. It's like, the first one's maybe 2 sentences, the last one is 4 sentences. But yeah. So for our case, it's a little special because we just want to show that Hamiltonian path in our constructed graph. Ultimately, we want to show it maps back to a Hamiltonian path in the original directed graph. And so it's going to have this kind of structure. This is a little of a bit of a caricature, but visit all the vertices, right? And so there's no particular direction in this because it's an undirected graph, but the endpoints are S prime and T prime. And within those there's S and T. And like say starting from S, it's going to have to do this in middle out, in middle out, in middle out pattern, because the only way to be able to visit all the middles along the way, if you're ending at T prime, right? You have to visit all the middles. Huh? Yeah, yeah. So we do the middle thing, and that gets us some undirected graph with 3 times as many vertices. And then we also add this super source and super sink gadget to that whole thing. Yeah, so that T prime, we have one T that's connected to everyone so that everyone can get there, but then we have one more T prime that's a leaf, so you have to end there. And that'll create enough asymmetry that we'll get what we want. Okay, good enough. Any questions? Yeah. Yeah, yeah. So let's go carefully through. So you want to show, yes means yes, no means no. There's different ways to do it. But one sufficient way is to show that if your input directed graph has a Hamiltonian path, then your undirected auxiliary graph will have a Hamiltonian path. This way, if your black box says no, it really means no for the directed graph as well. Okay. You also want to show, or the other direction is to show that a Hamiltonian path in your undirected auxiliary graph implies, in particular, we're going to map it back to a Hamiltonian path in a directed graph. Okay. This way, if the black box says yes, there is an undirected Hamiltonian path, that means yes, there was a Hamiltonian path in the directed graph. So that's probably the easiest one for ultimately you want to make sure that yes means yes and no means no, right? But if you can take Hamiltonian path in one graph and map it to the other and do the other direction, that will tell you that yes means yes and no means no. Yeah, so you just do that. The first thing we check is to even make sure that you guys tried both directions. And it's not uncommon to get a little confused and accidentally do the same direction twice. Yeah, so just like take your time. Uh, and then we know that sometimes it gets a little awkward doing all the details, so we try to be reasonable, but yeah, it could be sometimes a little cumbersome, right? So if we are doing, for us, the more cumbersome direction is going from showing that Hamiltonian path in the undirected graph is directed because you want to show that the undirected Hamiltonian path first has a certain nice structure. Starts at S prime, ends at T prime, and it has to go S prime S and then do this in mid out, in mid out, in mid out. So you want to establish that. That'll take like a sentence because if it didn't go in mid out, it wouldn't be able to visit the middle. That's what we showed. And then once you've established that it goes in mid out, in mid out, in mid out, then you can just read off the Hamiltonian path from the vertices in the order they're visited. Yeah, but it does require a little more care. Okay. Any other questions? Yeah, I'm gonna try to sneak in. Maybe it's a bad idea. So I try to sneak in one more topic. We have 5 minutes. Probably not, huh? Okay. Okay. Then I have some problems then. Okay. So, uh, instead of a Hamiltonian path, you can have a Hamiltonian cycle. Okay. That just means it's a cycle that visits everyone. It's a very closely related problem. Okay. And so I have 2 problems for you. One is, can you show that, I think this is a directed graph, but we could have done undirected. We could do it after. Uh, can you show that finding a Hamiltonian cycle is hard or get a polynomial time algorithm? I'm guessing your instinct is that it's going to be hard because it's so similar. But still, can you show that it's hard? Okay. And then the other direction, so I'll just tell you, it is hard, but can you show it? Because the other problem is, uh, can you go, and I'm assuming you're going to try to go from Hamiltonian path to cycle. And in this question is, can you do the opposite direction? Can you show that Hamiltonian path solves Hamiltonian cycle? Okay, so the first question is, can you use Hamiltonian cycle to solve Hamiltonian path effectively? And the other direction is the other problem is the other direction. The first direction is a little easier, that's why we put it first. Uh, but the other direction is fun too. Okay, so those are two questions. I can put the questions closer to each other so they're on one screen. Yeah. So let me maybe draw uh, some pictures. So you're given a directed graph, and what you want to know is if there's a cycle that visits every vertex. So it's like a Hamiltonian path, but starts and ends at the same vertex. Okay, but exactly once. So can you use that as a black box to figure out if there's a Hamiltonian path? Yeah. Yeah, so this one's pretty simple. You add a vertex that's connected to everyone and everyone's connected to it. So these are really bidirected, but okay. And so what's the idea? If you do have a Hamiltonian path that visits everyone, right? Then you just kind of connect the endpoints with S. Okay. Vice versa, if you find a Hamiltonian cycle going through S among everyone else, okay, so now your Hamiltonian cycle looks like this. It also goes through S. Now, if you remove S, you'll get a Hamiltonian path in the original graph. Okay, so that direction's a little easier. This one, the other direction, I think requires a little more cleverness, but it's not formidably hard. Okay, can you now use Hamiltonian path as a black box to solve Hamiltonian cycle? Yeah. Okay, so I'm going to take, let me just go slowly. So you want to take a vertex like this one and duplicate it. Okay, so uh, so here would be like two vertices, and are they going to have the exact same edges? Uh, so here are the same edges, and you want to flip one of them. Uh, I think I did that correctly. Oh, I'm missing these. Okay, it looks kind of confusing and chaotic, but so what's the idea? So you have a solver for cycle, and you want to figure out if this graph has a path. No, I got it backwards. You have a solver for path, and you want to see if it solves cycle. Wait, yes. Okay, so I'm just going to duplicate one of them. Okay, but now you have to explain to me what flipping means. Okay, so these are kind of matching. And the sloppier one is the new one. So what's the idea? Okay, so there's some path that includes both of these yellow things. I don't know. This is not represent. I mean, I just drew some random lines. So why does this path give me a cycle? It would be great if it started and ended at these some kind of copied vertices, right? So that is actually in the right direction. Yeah, that's what actually more what I had in mind. Uh, okay, how do I? Let's try it over. Okay, so what I kind of want to do then is I want to take this vertex and I kind of want to split into two. That didn't work. Uh, uh, what's the right way to do this? This is not going well. Sorry. Uh, okay, so we're going to replace this vertex with two copies. One copy gets all the in edges, which is this one and this one. Okay, so this is the incoming one or the sync one. I'll write sync version. And then this one is getting all the outgoing ones, right? So this will be the source copy because it only has the outgoing. And now if you find a path in the graph, a Hamiltonian path in the graph, it has to start at the source and it has to end at the sink.